Hello and welcome to this Eddy Advanced Features talk, or as I like to call it, the Eddy Extra Slice. I should stress immediately that this is for the nerdy. It is not part of the main course, and it's for you who are interested in learning a little bit more about the more advanced and more recent features in Eddy. So what are the advanced features of Eddy? Well, it's in addition to the things to be learned already, which is correcting for eddy current-induced distortions and gross movement, it's also trying to correct for movement-induced dropout, intra-volume movement and susceptibility movement. I will go through these one at a time and see if we can understand what they are and what Eddy is doing to try and correct them. So first of all, movement-induced dropout. So what is this? So what can happen? So we have the image encoding phase of our sequence, and we have the diffusion encoding phase or part of our sequence. Now, if there's any movement occurring during this part, that can lead to a almost complete signal loss in that particular image. And it's not hard to sort of imagine that this could be the case, because if you imagine what we are doing with these diffusion gradients here, this diffusion encoding, is that we are inducing a signal loss that is proportional to a tiny movement of the water molecules. So it's not difficult to imagine that a gross movement of the head during this part will lead to a signal loss, and that signal loss will be more or less even across the entire slice, because it's just so massive. It's a little bit more complicated than that, and it's actually only rotations that give rise to this, but that's just going too far. So what can Eddy do about this? Well, first of all, we need a little recap of Eddy. So if you remember what it does, it takes all the scans, it uses the current estimates to unwarp them, loads that into the prediction maker, and that's the loading step. Then it goes on to the estimation steps, and then for all the scans it gets a prediction out, it inverts the current transform, gets the prediction back into scan space, compare it to the scan, and use that difference to update the eddy currents and motion parameters. And what's important to notice or remember here is the fact that this comparison is done in scan space. So that's an important part. Secondly, so how are the predictions made? And again, as I said before, it's a Gaussian process, and all it assumes really is that the signal varies smoothly. So the way to interpret this is, so imagine you have the center here, and then any direction, any vector you can draw from this center, you can think of as the direction of the diffusion gradient of that scan. And then these points, they are simply data points. So this is all one voxel. This is obviously lots of directions. This is an HCP dataset. So if you want to know what the signal was observed in this voxel for a diffusion gradient in this direction, it turns out that that was the signal that was observed. Now, the way that Eddy models this is using a Gaussian process, and all that assumes is that the signal varies smoothly as we go around these different angles in space. And the predictions here are given by the surface, and the actual data points that we fitted this surface to are given by these data points. So you can see that mostly the data points and the predictions are quite close, as you would hope with any fitting. Right. So, detecting outliers. So what we have here is an example of someone who's actually lied quite still. So I said before, gross movement, but this could also happen as a consequence of the pulsatile movement on the brainstem. So what you see here is an almost complete signal dropout here, and this is caused by arterial blood shooting into the brainstem, pushing the brainstem forward, rotating it a little bit. So this is essentially a movement of the brainstem here, which has coincided with this diffusion encoding part of the sequence, and that has led to this signal loss. So remember that we do all the comparison in observation space, and that means that for each and every one of these slices we can compare the observed and the predicted. So, and then what we can do is we can just sum that up. So we can sum up the difference across all of these voxels. So if you look at this slice where there's no sign of any dropout, this is the difference between the prediction and the observation, and we have an average difference of 0.084. Over here, again, there's no real sign of any dropout, and this is the map of the difference between observation and prediction, but again we have a quite small average difference, minus 0.125. In this case though, we have quite a big area here with dropout, and we can see in the difference map, yeah, it's detected this area of sort of missing data, and it means that it gives us a much larger mean difference. Now, if you remember, so we get one of these mean difference values for every slice for every direction. So that means that we get quite a few of them, and especially in studies like the HTTP, for example, we have a lot of them. And that means that we can build this distribution of observed differences. We can then convert that to z-score. It's as simple as mean correction and variance normalization. We can convert that to z-scores. And then we can look for each and every one of these slices how many standard deviations away from the expectation being 0 in this case. So we can look and find that for each and every slice, and then we can use that to determine which of the slices in which volumes we believe to be outliers. And this is just to look at the distribution of outliers across volumes. So what we have here is 300 volumes, and we can see for this particular volunteer, which I think, I'm not going to mention their names, but I think he was one of the people who worked with the HCP. So he was a trained volunteer, he was able to lie very, very still. So there's essentially no movement at all in this particular data set. And that's the reason why all of these outliers are in the quite basal slices, because all of these outliers are of the type where you actually have a pulsatile movement in the brainstem, which is called the outlier. So this is just the outliers. So these are the volumes with outliers, and this is the slice you can see which has had that outlier. And what we can do then, if we observe one of these outliers, is that we can replace this slice with a prediction. And I'll go into later why we do this and why we don't just say, well, don't use this data, but I'll go into that later. So we can replace that with a prediction. So the question then is, how do we best make this prediction? Well, it's important that you think about this a little bit. Well, you don't need to, but I had to in order to implement this. So this is an example of just some data, and I've just simulated an outlier in this particular data cloud. So this is the outlier, and this is obviously now an outlier with additional signal, which you never actually see in real life, or you shouldn't see in real life. But the reason I've chosen this to be a sort of a positive outlier is because it just makes it much more easy to use a C compared to if I put something inside this sort of cluster of points. So we have an outlier here, and this outlier is far away enough from the surface that it's detected as an outlier. So now we want to know, okay, so what should we replace this outlier value with in this particular voxel? Now, if you look at the prediction here, this prediction has actually been affected by the outlier. It's sort of pulled out like a little nose on the predictions. So we don't want to replace it with that value. So what we want to do is we want to detect the outlier and then refit the model, this time without using that outlier. So I now refitted the model without that outlier, and you see now the predictions in this area are actually given by the surrounding points instead. So now I can take that prediction there and say, okay, that's the prediction that I want to replace this outlier with. So let's go into Eddy Revisited. So remember, as before, we have the loading step. Now we get to the estimation step. And in the estimation step, we start out as before. We get a prediction. We invert the current transform. We get the prediction in scan space. We compare it to the scan. But now we use this difference to update the eddy currents, the motion parameters, and a list of outliers. And the reason we have this list of outliers is, so essentially, a given slice, all of them starts out as being non-outliers. But then at the first iteration here, for example, we detect, oh, here's an outlier. So what we do then is we take that slice, then the original slice, the original data in that slice, and we move that into an outlier list, and in the data itself we replace it with the prediction. But then the next time we come around here, we do again the comparison, and we again base that comparison on the original data that was in the outlier list. And the reason that we do that is because sometimes if you have lots and lots of big movement in the data set, it means that in the initial iterations here, you can have something that ends up on the outlier list, not because it's actually an outlier as in having lost signal, but because it's so poorly aligned with the rest of the data. And as we go through the iterations and it gets better and better aligned with the data, something that looked like an outlier in the early iterations might no longer look like an outlier, and then we want to be able to bring it back. Right. So the next question then is, why do we replace the missing data with these predictions instead of just labeling the missing data as missing data to make sure that it doesn't affect subsequent analysis? So okay, I'm gonna just let you watch. Oops, that doesn't. So that should be a movie. It is a movie. Okay. So you can watch that while I'm trying to explain. So the data that is lost as a consequence of this movement during the encoding phase, that data is irrevocably lost. There's no way of getting it back. We just can't get it back. The only thing we can do is to make sure that it doesn't affect subsequent analysis, i.e. that these outliers doesn't cause us to draw the wrong conclusions in terms of direction of fibers or the magnitude of the FA or things. So one way would be to just say, okay, this data is lost, don't use it. Now the problem with this is that we also have the gross movement to take into account. So what you're seeing here is a slice acquired a little bit in to a diffusion protocol or diffusion sequence where the subject has moved. So the subject has rotated its head relative to its original position. That has now been rotated back into the reference space, i.e. into the position of the very first volume. So what we have two outlier slices in this data set, and you can see that they turn up as these dark bands. And that's because those slices that were slices in, so the original orientation, once we rotate this, they turn into not just a slice of loss, but a sort of a broad band where in the middle we have a complete loss, and as we go out towards the sides, we have an interpolation between data that's lost and data that's actually there. So if we were to just label things as lost, we would have to label a number of slices as lost. I mean, all the ones that are affected by the interpolation of this. So instead what we do is we take the actual lost slice, we replace that by predictions, and then we can use this in the rotation. Now, I should also stress that the particular prediction that you get, that is essentially the prediction of that direction predicated on all the other data in that particular box or in that particular data set. So it is the prediction that if you put that in makes the absolute smallest change to whatever processing you later want to do on that data. So it's just, so what we're doing is we're not recreating data. We can't do that. Data is forever lost. But what we can do is make sure that that loss is not affecting subsequent analysis. And so how accurate are these predictions? So what we have here, I'm just presenting here some simulated data, and it's simulating using something called POSSUM, which is a very, very advanced MR simulator. And what we have here is just some simulated diffusion data with occasional outlier slices, and we can see before and after outlier replacement. And this looks good, but is it the truth? And we can just look at different, so in this case, because it's simulations, we know the ground truth, so we can just look at what the outlier is, what it looks like, what Eddy guesses that this slice should really have looked like, and what the ground truth from the simulations was. And you can see that that looks fairly, convincing. Again, this is simulated data. And what you have here, you have simulated data with outliers, and those are the solid lines, or without outliers, and those are the dashed lines. And what this means is simply how many standard deviations away does a slice have to be before we consider it an outlier. So we've trusted 3, 3.5, 4, 4.5, and then infinity. That means that we never ever detect anything as an outlier. So this is essentially without outlier replacement. So dashed line is the data without outliers, and solid line is the data with outliers. And you can see if you don't do any replacement, it's actually quite a big difference. Whereas if you do replacement, there is very little difference, or at least considerably smaller difference between the data without any outliers and the data with outliers. So we're doing, we think, a fairly good job of correcting for this. And this is just an actual example. It's an 8-year-old who gets tired towards the end of the scanning. So you can see as we go further here, we'll have more and more outliers because this little 8-year-old is moving more and more. And after outlier detection, you can see that there's essentially nothing left of these outliers. So here's the movement coming in. And all you need to do in order to use this outlier detection is to just add --repol. So repol stands for replace outliers. So that's, you as a user, that's all you need to do. Second thing that is that Eddy attempts to correct for is something called intra-volume movement. So what is intra-volume movement? So normally, the way we normally do motion correction in fMRI, for example, and earlier also in Eddy, is sort of predicated on this assumption. Because if you remember how data are acquired, so EPI data are acquired slice-wise. These days we have multibands, so it can be groups of slices, but still, you think of it as slice-wise. So you start out, you acquire one slice, and then the next slice, and then the next slice, and then the next slice, and the next slice, and that's the volume. And then you go to the next volume, and you do the same thing. Now, if we only correct for volume, for movement that happens between volumes, then what we are doing is we are implicitly assuming that the subject is perfectly still as you acquire all the slices, and then if the subject is going to move, it does that movement exactly when we are switching from one volume to the next, and then the subject is perfectly still while we acquiring all the slices again, and then if it's going to move, he moves exactly when we go from one volume to the next. And obviously this is not a correct assumption. But another thing we can also note is that the fact that motion correction on the whole works as well as it does, it means that it's actually not such an awful assumption as I make it sound now. And the reason for that is that it tends to be that movement is mostly relatively slow and gradual compared to our typical TR, that would be like 2 seconds, 3 seconds, 4 seconds, something like that. But I say mostly because once you start scanning children, people, elderly, maybe demented subjects, then it becomes a real problem. Okay, so what happens if this is not true, i.e. if the subjects move while we're acquiring a volume? So this is the brain we set out to image. Then what we do is we acquire the first slice. But now what happens is that the subject moves. And then we acquire the second slice. So the second slice we have acquired has been offset relative to the first slice. And the subjects keep moving, and the subject keeps moving, and the subject keeps moving, and the subject keeps moving, etc. So what we're going to end up with is we're going to end up with an image, or a 3D volume image, of a brain that is quite severely distorted because of these movements. And I should say as well that for diffusion, typically, so what I showed you here was what happens if we have a sequential acquisition of the slices, i.e. we start with slice 0, slice 1, slice 2, slice 3, etc. Typically in diffusion, you have something called interleaved acquisition, and that means you start with slice 0, then you go to slice 2, then to slice 4, then to slice 6, until you've done all of the brain, and then you go back and you do slice 1, slice 3, slice 5. And that means that when you actually see this kind of intra-volume movement in diffusion data, you see that as a very characteristic zigzag pattern. Because of the difference in location between the odd slices and the even slices. Right, this might seem like a difficult problem to solve. And it is and it isn't. So figuring out the movements is not really that hard. And the reason why it's not really that hard is that what we have inside Eddy is a Gaussian process-based forward bundle. So if you remember, we can make predictions. We can make predictions for a given volume for all the slices. So we can predict exactly what this brain should look like. And then we want to compare that to what the acquisition actually looks like. And what we can do is we can actually, in this comparison, we can predicate any movement through time. So what I have done here is I've indicated, so it's slice 1, slice 2, slice 3, and the subject is still slice 15, slice 16, and then what's happened here, or what I predicated here, is that the subject then moved between slice 16 and slice 17. So slice 17 is now going that direction, slice 18 is going in that direction, and we can then go on to acquire the rest of the slices. So we can actually predicate or postulate any path of movement through time, and then look, what would the data that we acquired for this volume, remember this is the predicted volume, what would the data look like for this volume if the path of movement through time was like that? And then we just go and compare that to what it actually looked like in the acquisition. And we can just keep doing this until we have the best match to the acquisition. Now obviously this means there's a lot more parameters to estimate, because you are now not looking for one X translation. We are looking for potentially one different X translation for each and every slice, or we are looking for a smooth path of X translation through time. But still, the principle is easy, so that's not actually hard. The problem that's hard is that we end up with sort of wedges of missing data. And again, this is exactly the same example as before, where the subject, so we're acquiring first this lower part, and we get up to this point here, and the subject has been lying still all the way up to here. Now what happens is that the subject looks up. So after we acquire that, the subject looks up. And that means that this forward part, or this frontal part here, that we had already acquired, when the subject looks up, that means that ends up above the already acquired part of the volume. So we then go on and acquire that part twice. So this yellow wedge here, we acquire that twice. But the red part here, or this red wedge here, when the subject looks up, that means that this part here that hadn't been acquired yet, when the subject moves, that is moved down below where we continue to acquire the data. So we have a part here that's been acquired twice, and we have another part here that hasn't been acquired at all. So the way we're solving this, the way we're trying to solve this, is through a hybrid resampling. So each and every slice is complete. We have complete information about each and every slice, but each and every volume is potentially not complete. So what we're doing is for every slice that we've acquired, we resample that, so that we have a resampled slice on a regular XY grid but we don't resample it in the Z direction. Instead, we just calculate what the location should be in the X direction. So then what we end up with is we end up with a number of columns in the Z direction where we have data sampled at irregular intervals, and then we just fit a spline to that. And for those parts, for those bits where we have missing data, we can see that, okay, so we acquired that point, we acquired that point, we acquired that point, we acquired that point, but then we get here, oh, we didn't acquire that, we didn't acquire that, we didn't acquire that. So then we can go into our predictions again, and we asked this before, our predictions, and say, okay, we didn't actually acquire these 3 points here. Well, let's use the predictions for those 3 points, and then we go on. So it's quite a gentle way of replacing only exactly precisely those missing data points in selected columns with the predictions. So let's just look at what this looks like. So what we have here is a subject. This is an elderly subject. There's lots of movement. We have therefore lots of dropout slices, as you see. We also have intra-volume movement. So there's a lot going on in this data set, you see. And seeing this data set, you would probably say, well, this is a lost data set. I don't think we can do anything with this. So let's see. So first of all, we do just a correction for eddy currents and movement. We don't do any outlier correction. We don't do any slice to volume realignment. We see the gross movement has been corrected, but you can still see all of these. There they come. Lots of outliers. Then what we do is we do the same correction, gross movement, eddy currents, but we now do outlier replacement as well. And you can see, okay, it's already looking better, but there's still the odd volume here where you can see sort of a zigzag pattern. There, yeah, there's the odd volume. And this zigzag pattern there, that is where we have movement within the volume. So now we're also applying this intra-volume movement, the slice to volume correction I just described, and this is what it looks like. So, and if you look at the right hand side now and the moving the right hand side and compare that to the moving the left hand side, I'm sure you agree that it's quite a stunning difference between them. And this is just showing one of these volumes where we have intra-slice movement, intra-volume movement, and where we're correcting this just to show that we're not actually just making up data. We are really moving data from the place where it is to the place where it should be. And again, it is trivial for you to use this yourselves. All you need to do is to add this --MP order equals 16, for example. And this is just an example. So what MP, so MP stands for movement parameter, and order is just order. So regular volumetric motion correction, that will respond to MP order equals 0. So that's the 0th order. If you set MP order to 1, then you're also modeling any linear movement during a volume, and then as you go to higher and higher number, you are using a higher and higher degrees of freedom for this path of the movement through time. And what I would recommend here, because it used to be that it took a long time to run this with high orders. It doesn't anymore because we changed the way we do things internally. So what I would recommend is just use a reasonably high number, but make sure that that number is lower than the number of excitations. And what I mean by number of excitations is, if you're not using multiband, then the number of excitations is the same as the number of slices. If you are using multiband, then the number of excitations is the same as the number of multiband groups. Okay, so that was slice by movement. No, I've seen in intra-volume motion. Oh God, I'm getting tired. There we go. And finally, what we're going to look at is something called susceptibility by movement. And in order to explain this, I will just start out by showing you again some simulated data. So this is simulated data with lots of movement. I'm just going to run this for a little while just so you get a chance to see the kind of movement in this data set. So you can see that it's rotation around the y-axis and it's rotation around the x-axis, quite large rotations. So what can Eddy do with this? Well, so on the left hand side you see a slice quite high up before and after motion correction using Eddy. And you can see it looks like Eddy's done a reasonably good job. But if we then go to a lower slice, and now I want you to look at the after picture here. So it starts out looking all right, the after, but there you see, and there, oh, look at that. So clearly there are things going on here that Eddy is not able to correct for. So what is it that's going on here? Well, what it is the magnetic field, either the susceptibility induced off resonance field, changes when the subject changes its location in the scanner. And not only that, it's only certain movements in the scanner, so certain subject movements, that will change the field. And those movements are the out-of-plane rotations. So I'm going to try and give you this picture. So normally what I do is I wave my hands around when I explain this, but I'm going to try and explain this without you actually seeing me moving or waving my heads around. So think of the magnetic flux of the field as a very slowly moving river. So it's a very slowly moving river, and that's the magnetic flux of the field. Then think of your hand as the object that is perturbing this field, and you think about taking your hand and sticking it inside the water, or in the water, in this slowly moving river. So what's going to happen is you're going to have a disruption of the water around your fingers. Now imagine that you are just moving your hand sideways, perpendicular to the flow of the river. What's happening then is that you are perturbing the river in exactly the same way as before. You're only moving the point in the river where you're perturbing it. The same if you move your hand downstream, or if you move your hand upstream a little bit. Again, you're perturbing the river in exactly the same way, but you are just moving it a little bit. And that's what's happening in the scanner. If you do a pure translation in the scanner, i.e. just moving your head to the side or moving your head out of the scanner, what you're doing then is you are still perturbing the field in exactly the same way as before. The only difference is that you have moved the location of that perturbation. And we say then that, okay, so the field is the same in the framework of the subject. So the field simply follows the subject. But now go back to your hand in the river, and now imagine that you rotate your hand around an axis that is not the direction of the flow. So imagine that you just rotate your hand a little bit around an axis that is not the direction of the flow. Now you can see that you are now disrupting the river water, the river, in a profoundly different way, because the way that the water now hits your hand is different. And that's the same with the head in the scanner. If you rotate your head around an axis that is not parallel to the magnetic flux, i.e. if you rotate around the x-axis or the y-axis, then you will change the field. So you've seen, so you now have a brief explanation for why this might happen. You've seen that simulated data. You might think that simulation was exaggerated, and yeah, it was one of the worst cases, obviously. But what I'm going to show you here is an actual HCP subject, and this is after having done all the corrections to this data. And you can see towards the front here how it appears Sorry about that. That was our phone. Yeah. So it appears as the frontal parts here is changing a shape, but it's not. It is precisely this, that the susceptibility-induced field is changing in these parts here. And this, I mean, the reason it looks like the subject is lying still is because we've corrected for all other things, that we've corrected for the gross movement. But, originally there would have been a lot of movement in this particular subject. So the problem then is that we no longer have, as we assumed before, just a single susceptibility-induced field for the whole study. And potentially we have different susceptibility-induced fields for every location, for every volume. And that becomes completely intractable. There's no way that we can calculate a separate susceptibility field for each and every volume. So how can we make this tractable? Well, it looks like the rate of change of the field with respect to these rotations. So this is rotation on the x-axis, and this is rotation around the y-axis. It looks like the rate of change of the field is actually linear, roughly linear, with respect to these rotations. So that means that maybe we can use a low-order Taylor expansion. And what this means is that we say that, okay, the field for any location or for any of the volumes, there's a volume 2 here, that is roughly the reference field at volume 0 plus whatever rotation took place between volume 2 and volume 0 multiplied with the rate of change of the field with respect to rotation around the x-axis, so theta around the x-axis, plus whatever rotation took place around the y-axis between volumes 2 and volume 0 multiplied by the rate of change of the field with respect to rotation around the y-axis. And we can just go on. So what we've done now is that we have reduced down the problem from thinking about trying to estimate a unique field for each and every volume to just estimating these two rate of change fields. And I'm going to go back here, so you see these slopes here. So these different locations here, or these different plots here, they correspond to the different locations in the image here. So what you can see is that we have a different slope. So we have a different slope for each and every one of these locations. And the meaning, or the interpretation, how to interpret this derivative field, is that the value for each and every voxel is the value for the slope of that plot in that particular voxel. So this is for the slope in the left-hand side, where we have with respect to x rotation, and this is for the one in the right-hand side, where we have with respect to y rotation. Okay, so how then do we go about estimating these two, the rate of change fields? Well, first of all, we need a forward model for the observed changes. So we set up a model where the observed differences, and this is predicted minus observed, for all the volumes, and this as you know, for the HCP dataset, this could be several hundred. For your own dataset, it might be 60 or 100 or something like that. So we set up a model where the observed differences, after we have corrected for everything else, can be explained by rate of change per degree rotation multiplied by the rate of change per degree rotation, which is this, multiplied by the estimated degrees of rotation. And this is for the x rotation, and this is for the y rotation. And the way this works, so this is the rate of change field that tells us how to move the sampling point, because remember what a susceptibility field is. It is essentially is a scaled displacement field. So this is how to move the sampling point multiplied element-wise with the gradient of the image in the phase and co-direction, plus, and this is important. So this is what happens when we change the sampling point, and then plus this contribution, and this is how we change the compression or expansion of a particular region as a consequence of changing the field according to this, multiplied by the image itself. So this is the forward model, and these are the ones that are unknowns, and it's actually just that and that are unknowns, because this can be calculated from that one, and this can be calculated from that one. So these are the unknowns. And what we do is we simply set this up as an overdetermined system of equations, and because you have now seen so many talks about the general linear model, I just say that this is exactly the general linear model. This is precisely the general linear model. So this is a design which essentially tells us the predicted causes of the difference, and here we have some unknowns. And these unknowns, what they are the parameters of a basis set that is used to model these fields, so these unknown fields. And the basis set we're using is simply a set of splines. And then what we do is we solve this in exactly the same way as you saw solving the general linear model earlier. One difference to the general model you've seen is that this is now iterative, and this is iterative because these rate of changes that you have here change as we change the estimate of this. So we have to do this a few times, maybe 5 or 10 times. And what does it look like now? So this is the simulated data. So that was before, after, and this is with susceptibility to movement changes. So estimates. So what you're seeing here is you're seeing that here after, so you're seeing these quite big changes even after we have corrected for everything else. But if we do include the susceptibility by movement, you can see that this is pretty much gone. And this again is from the simulated data, and this is just to show. So this is the ground truth derivative field, and we again, because of simulation, we know the ground truth, and then we can estimate these, and this is just to show that we can actually estimate it without eddy currents and with eddy currents, because estimating this in the presence of eddy currents is considerably more difficult. And just to look at the problematic HCP subject, so you can see this before, and you can see these quite large changes in shape. And after we've done this, these are, I would say, reduced by 90% or something like that. You can see that there's other things going on, and that's what I'm currently working on, but that is not movement by susceptibility. Okay, and I've actually forgotten, I realized now, to include a slice where I'll show you how to turn this on, but just go to the online documentation and you'll see it there, and I'm sorry about that. And that was it. Thank you very much.